If at is positive, then the linear speed will keep increasing. So it's accelerating. If at is negative, then the value of v will keep decreasing as it is moving around the circle. Now let's take an example of case 2 where the value of AC is non-zero and tangential acceleration is 0. So imagine we have an object moving in a horizontal circle. So consider a table. On the table, we have a ball which is connected to a string, and that ball is moving in a circle. So this is an example of a horizontal circle. If the speed of the ball is constant throughout the circular motion, we can say it's a uniform circular motion, which would mean AT is 0 and AC is not 0. Case number 3, where both AC and AT are non-zero. We already discussed this is object moving in a non-uniform circular motion, which means the variable speed. And the example for case 3 is motion of an object in a vertical circle. So let's analyze. Imagine we have a ball connected to a string and it is moving in a vertical circle where v1 is the linear speed at the bottommost point. Now, let's read this. The Earth's gravitational force causes the object's velocity and the tension in the string to vary in magnitude from the lowest to the highest position. So, as this ball goes up into the circle and goes to the topmost point, as the ball completes this trajectory, the speed will keep on reducing because of gravity. So for instance, if I consider this particular point and we draw a tangent, that will give the direction of linear speed, so v2. And at the topmost point, if we draw the tangent, that would give us v3, which is the linear speed at the topmost point. Now, like discussed earlier, because of gravity, the magnitude of speeds will keep on reducing. So we can say v1 is the highest and v3 is the least. So v1 greater than v2, which is greater than v3. Understanding case 3 in a little more detail. So this is a case where centripetal acceleration and tangential acceleration both are non-zero. So how do we find the total acceleration? Since you have two types of acceleration here. So what do? Go back to the basic concept. The total linear acceleration of an object moving in a circle is the vector sum of centripetal and tangential acceleration. So how do we do that? The direction of AC is always towards the center and the direction of AT is tangential. So how do we find the resultant? AC and AT, if we can create a parallelogram using the parallelogram law of vector addition and then draw the diagonal. So that diagonal will give us the direction of a net. So we can see this red arrow will represent the net acceleration of this particular object. And how do we find the magnitude? Since AC and AT are perpendicular to each other, we can use the Pythagoras theorem to get A net. So A net is equal to square root of AC square plus AT square. So this is the total acceleration of an object which has both AC and AT. Steps to solve questions of circular motion. So there are 4 steps which we have to consider. Number 1, we need to draw the free body diagram of the objects, which means basically just show all the forces which are acting on the object. Number 2, identify the centripetal force. And how do we do that? Net force which is acting towards the center of the circle. We will understand this with a few examples. Then step 3 is apply the entire centripetal force equation, which is Fc is equal to mac. And then we can apply the two types of formulas for AC, which is either V square by R or R omega square. And step 4, which is the last, we need to balance all the forces in a direction where the object is not accelerating. So we are going to apply all these 4 steps in different types of questions. So what are the possible circular motion question types? Case 1, a horizontal circle where the ball might be connected to either a string or a rod. So basically it's a horizontal circle. Case 2, it's a vertical circle where the ball is connected to a string or a rod. And case 3, it's a vertical circle only, but the ball is not connected to a string, but the ball is rolling on a circular path. Let's take up all these cases one by one, starting with case 1, which is a horizontal circle. So imagine we have a table. On that table is a ball, which is connected to a string. And let's say the string is fixed at a particular point. Now imagine the ball is moving in a circle on this table. Now, since this table is horizontal, which means the circle is also horizontal. And now let's apply the 4 steps. Step number 1 was to draw the free body diagram of this object. So the number 1 force is the gravitational force, which is the weight mg acting downwards. Then, since the ball is in contact with the table, we have a contact normal reaction N pointing upwards. Also, since the ball is connected to a string, that means there is tension in the string as well. So, there are a total of three forces acting on this ball. Step two, identify the centripetal force. And how do we do that? The trick is net force, which is acting towards the center. And among all these three forces, there is only T, tension, which is acting towards the center of the circle. So centripetal force here is T, tension. Now, please remember as a rule, in the free body diagram, you do not show FC. But the catch here is certain forces will act as the centripetal force. So, like in this case, T, the tension which is acting towards the center, is the centripetal force. Step 3, we use the entire centripetal force equation. So here Fc is equal to T. So I'll write Fc is equal to T, which can be written as mv square by r or mr omega square. And finally, step 4, we need to balance all the forces in a direction where the object is not accelerating. If you analyze the motion of this ball, it's moving on the table. So the ball is not going up or down. Now, since the ball is not going up or down, so the upward force needs to be equal to the total downward force. So here N, normal reaction, should be equal to the weight. So N is equal to mg. That is the step 4. So this was case 1, a horizontal circle. Case 2 is a vertical circle, but the ball is still connected to either a string or a rod. So let's analyze. Have a look at this diagram. We have a ball connected to a string, but this time the circle is vertical in nature. Now we will analyze different positions of the balls with respect to the entire circle. So in the second image, the ball is at the topmost point. In the third image, the ball is at some random angle theta. And in the last image, the ball is at an angle of 90 degrees. Now let's apply all the steps one by one. Step number 1 is to draw the free body diagram. Step number 2 is to identify the centripetal force. And step number 3 is to apply the entire equation. Let's start with step number 1 to draw the free body diagram of the object. If you analyze this first example where the ball is at the bottommost point, try to figure out what are the forces acting on this ball. The first force will be the mg acting downwards, and the tension will be away. Remember, the direction of tension is always away from the object. So in this case, it will go towards the center of the circle. And these are the only two forces which are acting on the ball. So that's step 1. Step 2 is to identify the centripetal force. How do we do that? Net force acting towards the center. So one might say that T, the tension, should be the centripetal force since it is acting towards the center. But it is not just T. T is acting towards the center, but mg is going away from the center. The catch here is we need to find the net force acting towards the center. Now, since T and mg are opposite, so we will subtract them. So the net force will be T minus mg, which is the centripetal force. And then we can apply the equation. T minus mg equals to mv squared by r. Now, considering the second situation where the ball is at the topmost point, the weight mg always acts downwards. So even in the situation 2, mg acts downwards. But remember, the direction of tension is always away from the ball. So in this case, going away from the ball would mean going downwards. So tension will be downwards. So step 1 is done. Step 2 is to identify the centripetal force. So here mg and T both are acting in the same direction. So the net force will be addition of these two. So we will write the centripetal force in this situation will be T plus mg, and then we can write the original formula. T plus mg is mv squared by r. Now this third case is a little tricky. Step 1 stays the same. Draw the free body diagram. So mg acts downwards and the direction of tension will be away from the ball and acting towards the center along the string. Now, how do we identify the centripetal force? Remember the rule, it's the net force acting towards the center. So T is definitely acting towards the center. But mg, it is neither acting towards the center or away from the center. So what do? We will have to break this mg into two components. So this particular component will be mg cos theta. Reason being, if this particular angle is theta, so this particular angle where the cursor currently is, this is also theta. So if mg is acting downwards, this particular component should have the cos parameter. So this is mg cos theta. And the other perpendicular component of mg will be mg sine theta. Now analyze, T is acting towards the center, but mg cos theta is acting away from the center. So like in the case 1, here also we will subtract. So the centripetal force will be T minus mg cos theta. And that is the centripetal force. So we can apply the entire equation. But remember, in this case number 3, mg sine theta has no role to play in centripetal force. It's only T which is acting towards the center, and mg cos theta which was going away from the center, that will account for the centripetal force. Now in case number 4, where the angle is 90 degrees, so all we need to do, just put theta is equal to 90 in this equation. So cos 90 is equal to 0, which means the centripetal force will be T only. So in the last case, where the mg is acting downwards and the direction of tension is towards the left hand side, since the angle is 90 degree, cos 90, remember, is 0. So we can say the centripetal force will be equal to T, and T can be written as mv squared by r. And these are the 4 cases of vertical circle which we have to consider.